In this video, I'm going to continue working on practice questions for grade 12 general. We're moving on to topic 2, which is about charges. So looking at this one here, is asking about what is true about the spheres. If this is a negative charge, it means it will repel the electrons. If there is an electron here, it will repel to the other side. All the minuses will come here. What will remain are the positive charges, protons. Just remember, protons don't actually move. Even if you were to say they're going to be attracted, protons don't move. They're too big and heavy, and they're stuck inside the nucleus. It's the electrons that either move away or move towards. Anyway, the point here is that this will have a positive charge, this will have a negative charge, which is why the answer is B. However, if I decided to change the question a little, let's see what would happen if I said this was going to be a plus charge. Plus. If that's the case, what you will find is that this will attract the electrons to the side over here. They will attract the electrons. This will become minus now over here, and this will become positive. So now we have this minus and plus, and you would figure out which option that would be. In that case, it would be option D. So those are the two different scenarios. Just follow the path of the electrons. You of course know plus and a minus will attract, a minus and a minus will repel, a plus and a plus will repel. Okay. Now we have this little electroscope, and this is a charged rod, and you're asked to see what happens depending on what charge the rod is. So let's see what happens. If I already have a positively charged electroscope, these are kind of already repelling, which means this will be a positively charged rod. What will it do? Remember, even though this has got positive charge, it does not mean there are no electrons here. It just means there are more protons than electrons. We do still have electrons there. There's many, many, many. So the few electrons that were there also come up and join. So that means this leaves, well, more positive spaces over here. The electrons have left. This becomes more positively charged because the electrons have joined the party up here, which means they will repel more. They will move further apart. So you will say they will move further apart. However, if I change this around and go to the next one, which is minus negative charge, what happens? Well, more electrons from here, some of the electrons that would have already been here, will come down and join over here. And these pluses will be met with some more electrons, which will neutralize them, so they will repel less because we have more electrons down there too. So they will fall because of this. If you have the electrons, it will cancel out some of the positive charges. Very nice. Next, Q equals NE, which is not a possible value for the net charge. So you just need to remember that everything that has a charge has to be in multiples of an electron. You either have one electron, or you have two electrons, or three electrons. You don't have anything in between. You don't get half an electron or a quarter of an electron, 0.3 of an electron. No, it's either 1 or 2 or 3, which means it's either 1.6 times 10 to the minus 19 or double 1.6, 2 times 1.6, 3.2, and so on and so on and so on. So you need to know that everything is an integer multiple. That's what they say here, integral multiple. Anyway, what are we saying? All we're saying is we need to figure out which one is not a possible number. So these are all in times 10 to the minus 19, so is the electron charge. So if I'm going to figure out which one's not true, I just divide each one of these numbers by 1.6. I will do N equals Q over the charge of the electron. I can write minus 8, doesn't matter, that just means it's negatively charged. Minus 8, I'm going to divide that by 1.6. What do we get if I get minus 8 divided by 1.6? 8 over 1.6, I will get 5. So that is 5 electrons. Electrons, that's fine. 3.2, I've just mentioned that. 3.2 is 2 electrons. 4.8 divided by 1.6 would give you 3 electrons. That's 5 electrons. This is 2 electrons. 3 electrons. What happens if I do this next one? 8.8 divided by 1.6. I get 5.5. Not allowed. 5.5 is not possible. This is the answer because it asks for which one is not possible. I hope that makes sense. Next, we're moving on to this question here. We're talking about the direction of the force. So now we have a negative, and a negative. We want to know what happens to this charge. Where will he go? So we know negatives, they will both repel from each other. So this C and this A do not like each other, so he will run this way and he will run that way. They will go in opposite directions, and that's the way that they would write, the opposite directions. We got this B as well. This B will run away from this C. So this is on the same line of action. They will be in opposite directions. Now I have two arrows, one going up and one kind of going down. The result will be in between them. The result will be something like this. And you would know that with vector addition. You take one arrow, start with one arrow, and then you move over to the next one, and you will do that. Take this arrow, bring it over here. This is the direction, to the right. That's why the answer is to the right. Let's change it up a little. Let's make something else up. Let's say I introduced another charge over here. Let's say I placed a positive charge. I'll keep that as minus, and I'll make this one also positive. Now, this is something that could happen in your exam. They won't be exactly the same, so you should be able to understand each scenario. So according to this one over here, where will he go? So he will be attracted to this one, right? So he will go towards him. And of course, this will be attracted, but I don't care about him. I only care about this one. He will be repelled by this one. So he will be repelled, which means he'll go that way. And this one will go that way, opposite each other. And clearly you can see here, the result will be somewhere up along straight. Again, you can take this arrow, or this arrow, doesn't matter, but if I take this arrow and I move it that way, and I join the arrows together, tip to tail, I will see my result going upwards. That means the answer would have been D. Okay, let's continue. Over here, we need to find the magnitude of the force between two charges. Now, if you're stuck again and you don't know which formula to use, check. Head over to the formula sheet. And let's see. Clearly, we're talking about charges and things, so we're not over here anymore. We're going to be looking down over here. This is where I'll be looking. Now, what do I have here? I have two charges, and I have a distance between them. Well, there's only two formulas, by the way, for force. There's this one, and there's this one. This one's not good because it's one charge. This one's good because there's two charges and a distance. Look at that. We have an R as well. This thing is annoying, this black thing. We have two charges and a distance. This is clearly the formula that we're going to use. So that's what we'll do to get to 2 marks. Well, actually, this is a multiple choice, so there's no part marks. But anyway, now you know how to solve it. We will use F equals K Q1 Q2 over R squared. Now, you might forget what K is. Not a problem. Scroll up, look at the formula sheet. Coulomb's constant is written there for you. Coulomb's constant is right here. Also, if you wanted to know the charge of an electron and you forgot, it's also here for you. So that's given to you. You don't have to memorize that number. Now, let's put the numbers in. 9 times 10 to the 9, and I'm going to multiply that by the charge 1. 1 times 10 to the minus 6, 1 times 10 to the minus 6. Again, 1 times 10 to the minus 6. And I'm going to divide all of that by the distance, 0.40 squared, because it's squared here. Put that in a calculator. Hopefully you get a small number, 0.056, something like this you will get in your calculator. Very nice. An electric field is pointing downwards. You have a value. What is the direction of the force on a positively charged particle? So what does that mean? All right. If it's an electric field pointing down, I will draw some arrows going down. If I'm going to draw some arrows going down, I know that it goes from plus to minus, right? Field lines go from plus to minus. So if I have a plus like this and a minus like that, that's my field. Where will a positive charge go? Well, a positive charge is attracted to the minus. The positive charge, in this case, will move downwards. That's why it's down. If I said to you negative charge, it will move up. Another variation of this question could be an electron feels a force going to the right. What is the direction of the electric field? What is the direction? So if you're going to do this, you can just draw 2 plates. This is attracted to a plus, so over here I will write plus. That means this is repelling with a minus, so this side must be minus. And same thing, goes from plus to minus, right? The direction of the field, in this case, would be to the left. You can write the word left. So just a little extension there for you. Now, let's move on. What is the strength of the force on a charge? Look, we have an electric field. We have a single charge Going back to the formula sheet, scrolling over here, what force formulas do I have? This one and this one. Here we go, FEC, F equals EQ. That's the formula I like to use, FEC, F equals EQ. I will put the numbers in and get the answer for F. And you will have the E, 50, multiplied by 6 times 10 to the minus 6. And if you do that correctly, hopefully you'll get this answer here. Very good. Let's move on. Now we're going to apply the electric fields. This is not, well, we're still doing fields, but this is fields for a charge. All right. If you remember using FEC, we can actually derive this formula. It's not that hard at all. You have F equals K Q1 Q2 over R squared divided by Q. So one of the Q's will cancel, leaving me with just KQ over R squared. So that's where that formula comes from. But how do I know I need to use it? Well, let's see. What is electric field at a point from a point charge? For a point charge, look at that, written right there for you. So they're practically telling you which formula to use. For a point charge, KQ over R squared. Let's do it. E is KQ over R squared. K, 9 times 10 to the 9. You don't need to write the units in. 9 times 10 to the 9 multiplied by Q. 5 micro is minus 6. As I mentioned, it's important. Minus 6. Divided by 20 centimeters. Must be meters. Like I said, you can divide by 100. Nice and easy. 0.20. Why not? Squared. And you'll get your answer, 1.1. And if I want to know the direction, well, how can I figure out a direction? It's a positive charge. Positive charge points outwards in all directions. Positive goes outwards. So at point P, it is going away from the positive charge. If it was a negative charge and I had a point P over here, the direction would be towards because it goes into the negative. Out of the positive, into the negative, and just to extend it for you, they join together. You end up having a field line pattern that kind of looks like that. And that's what the field lines look like, which we've done already in class. And we're moving on to electric fields. Amazing. Which of the following is true for a single positive charge? I've just mentioned it. It is this one over here. This would be a negative charge. That would be negative charge. This should be a minus over here. That's why that's wrong. This is not true at all. It should be coming out or in, so that's not going to happen. This looks more like a field around a wire moving in and out, and we'll deal with that in another term. And this is a charge inside a field, so not true. This is the only one, plus with the lines going outwards. Okay, so let's move on. We're ranking these from A to B to C, which one's strongest to weakest. In this case, closest to the charge, closest between the lines, is the strongest. And you can see that A is right next to this charge, so this is definitely the strongest. And then you have an option B and C. B is close over here, further away, but however, the reason this comes next is because C, actually look, these lines repel. In fact, at C, you can say the electric field here is actually going to be 0. He is very well protected at C. So you can just remember that if they are repelling, the electric field in the center will be 0. So this will be the weakest. A, then B, then C. That's what we have over here. Now, a positive test charge moves further away from a positive test charge. So if I put a plus and a plus close together, they are not happy at all. They do not want to be next to each other. They have a lot of potential energy. As soon as you release them and let them go where they want, they run away. They run away until they run out of energy and they get tired, and then they can relax again. So that means they use up their energy running away. Positive and a positive, as they move away from each other, their energy will decrease because they're fine. They're not next to each other. They're not repelling. The repelling force is less when they're further away. You will know that if you take two magnets and you bring them close together, the north and the north, for example. It's hard to push them together. The force is stronger. But when you leave them further away from each other, nothing happens. And actually, what if I said to you a plus and a minus? What will happen now if I remove the plus and a minus away from each other? Right now, they want to be together, don't they? So they are happy. So if I move them away, they will become unhappy. They want to be together. If I had opposite charges, their potential energy will increase. They are attracted to each other. They will want to stick together. So that means their energy would have increased. So, long story short, positive and a positive or negative and a negative, separating them makes them happy because they repel. a plus and a minus, so minus and a plus. Separating them will not make them happy. Separating two best friends, they want to be together. The minute you leave the classroom, they will run back together again. This happens to me every time when I'm teaching my students. Anyway, let's move on to the next question. Now we're looking at this. We have two charged plates. We have a distance. We have a field. We need a potential. Well, let's check. Over here, electric fields, potential. We have a distance, electric field. V is W over Q, which I don't have. Force times distance over Q, I don't have a force. Or E times D. I have that. I have an E and I have a D. VED is the formula. This simply means V, we can use this part, or this part, or this part. We're going to use this part. Put that into the equation. We can get 1,800 multiplied by 1.5 centimeters. Remember, divide by 100 or times 10 to the minus 2. You will get that, and this is your answer. Whatever answer you get here, even if you got it wrong, don't forget the unit, you get this wrong and you use that answer over here in the next one, you will lose the mark here, of course, but you will still get full marks here. This is called error carried forward. So don't worry if you made a mistake up here. Whatever number you write, even if you don't know what it is, please make one up if you don't know at all. So you can use it here. So you can get full marks here. Now, how much work is required to move a proton? How much work? Well, work for a charge and a V is this relationship over here. W equals QV. W equals QV, a proton. It didn't say the charge, but it said proton. If it says proton or electron, you will use the number 1.6 times 10 to the minus 19 automatically. Whether it's a proton, that's positive, or an electron, which is negative. You would write the negative here because this is work, which is a scalar, and we will use the negative. It'll be negative work. It doesn't matter anyway. It's just we just want the value. Long story short, that's the answer. Very good. And last page, the final thing, which is true about the fields near a conductor. So if I have a conductor, something like this, I have a positively charged conductor. That means I have positive charges all the way around this plate. Positive charges around this plate, fine. The field line, remember I said, goes out in all directions, no matter what direction it's coming out. Look at this. That's perpendicular to the surface. That's 90 degrees. These are 90 degrees. It is always perpendicular to the surface, true. Equipotential, well, yes, that's a plus charge, that's a plus. They're all the same value of charges. This might be 10 volts, I don't know, the potential might be 10. This might be 10, that might be 10. They're all 10 because it's the same charge. This is true. The potential difference will become 0. Well, yeah, if I move from here to here, that's 10 minus 10. Potential difference, if you've forgotten, is just final minus initial. So 10 minus 10, 0. Move over to here, 10 minus 10, 0. Move all the way to here, 10 minus 10, 0. This is also true. 1, 2, and 3 are true. Final question here, you will most likely get one question on capacitance, and it looks something like this. You have a little capacitor, you have a potential difference here, you need to find the charge in this case. There's one formula for capacitance, and it's not going to be hard for you to figure out that the formula you're going to use is this one. Shift solve, or rearrange. I like to rearrange. Q equals CV, nice and easy. Microfarads. This farad is for capacitance. Microfarads. So you will write that for C. Don't be confused, because this C is coulombs, which is the unit for charge. Farads is the unit for capacitance. Okay, so that multiplied by that, you will get your answer. 35 times 10 to the minus 6. That's a 6. Multiply that by 50. Putting that into your calculator, hopefully you get this number here. Nice. Next thing, I'm just going to quickly go through the units for you. All of these units are meters. That's just degrees. N is just a number. It doesn't have a unit. Q, I can't write on this page. Can I write on this page? It doesn't look like I can. Maybe I can use this little thing. I will draw. Q we can use is charge, coulombs. Then I'll have to do it individually, one by one. And then number of electrons, no unit. F, newtons. R is a distance. R is a distance, so then for that distance I will simply use, or please let me draw, that will be meters. Electric fields, I cannot draw there. That's really annoying. Electric field is, well, if you forget the electric field, look, F over Q, newtons per coulomb. This is going to be newtons per coulomb. Electric field, you divide newtons, okay, that's annoying. Newtons per coulomb. Potential difference is V, potential energy and work, they are both going to be joules. This is V, this is V. This is force again, that's newtons. Right over here, force is force. Distance is meters. Capacitance is farads. Sorry I couldn't keep writing, it's just, it's not being my friend today. And that's us. Good luck with your exam. Thank you.